Good afternoon, engineer. My name is Oscar and my partner Lizeth. I am going to begin in the presentation first and second order dynamic system. Um, First order hydraulic system represented by a tank with a given area and hydraulic resistance. The objective is to analyze how the water level responds to an input flow using dynamic system theory and transfer function. This is the transfer function. Okay. And in this part of the lab, we analyze the effect of changing the bank area in the first order hydraulic system. Remember that the time constant of the system is defined as tau equal area by multiply RH. And it would keep the hydraulic resistance fixed and change the area. What we are really modifying is the time constant. When the area is small, the time constant is low, which means the tank level responds quickly to changes in the input flow. On the other hand, in this area it's large, the time constant increases, making the system slower and taking more time to stabilize it. Well, in the simulation, we see four curves correspond to areas 1, 2, 5, and 10 square meters. The blue curve with A equal 1 rise almost immediately to its final value. The red curve with A equal 2 is a little slower. The green and the purple curve with large areas show a much lower response, taking more time to reach to the same steady state level.
The code I present models the response of a mass spring damper physical system, which is a classic example for a second-order dynamic system. Mass represent inertia, spring provides the restoring force, damper introduce energy dissipation. In the mathematical model, we obtain a second-order transfer function. The defined parameters of the system are a natural frequency, is equal 5 radians per second. Damping radio is zeta equal 0.4. Respond to a unit step input. Initial oscillation to inertia, gradual damping until equilibrium. K metrics is the rising time, the peak time, setting time, and overshoot. The system is underdriven, showing oscillation that is stably quickly typical in suspension and structures where speed and stability are balanced. Two curves are compared with positive values of zeta, which represent stable system, and negative values, which represent unstable systems. In positive zeta, with zeta equals 0, the system oscillates indefinitely because there is no energy dissipation. With values between 0 and 1, the system is underdamped. It oscillates, but gradually the vibration decreases until reaching equilibrium. With zeta equal to 1, we have critical damping. The system don't oscillate and reaches equilibrium as quick as possible. With zeta greater than 1, the system is overdamped. It reaches stably, but more slowly. In negative zeta, when the coefficient is negative, the system becomes unstable instead of dissipate energy. The damper injects it, causing the oscillation to grow over time. This prevents the response for ever strings, which are unstable in real system.